First Spin. Welcome to First Spin, a show where I learn how to use the parallax propeller without having any prior programming experience. Rather than do this on my own, I have enlisted the help of Roy and Whisker.
She's making us do all the work.
Yeah,
It's
typical.
so easy. Hey!
So basically the idea here for those of you who are just tuning in this week for the first time is that Addie asks us questions that she has about the propeller, first spin, related topics, whatever, and we do our best to explain them in such a way that not only does she get an answer, but she's put on a good track to not only learning how to do this stuff, but learn how to do it really, really well.
Right.
Yeah, sometimes it takes 5 or 6 times of us answering before she gets it, but
She's
we make
kinda
sure she
slow.
gets it.
Repetition
You know.
helps for the noob. Well, for me. So,
Honestly, this stuff's really complicated, especially if you're not familiar at all with it. And Addie is not familiar with this stuff at all. So I mean, it's a good thing because, it's a nice blank slate to work with. She doesn't have any of the preconceptions that somebody who knows another programming language would have.
right.
So that does make some things easier.
Right.
Well, I would hope that it's not completely blank right now after so many episodes of explaining. It's got a little bit of stuff on it.
Yeah, I mean, a little bit of.
She's going to
meat
have
on the
fun
bone.
trying to learn C later on. She's going to be like, what, you can't do a DIRA?
Later. I gotta figure out spin first. All right, so last week I got some homework and we were talking through the cog-ram map, through the special purpose registers, and we had started talking about DIRA and my program with my LEDs turning on and off.
So these special purpose spots are basically memory in each one of the cogs. And by reading or writing to these special places, you can do things
Like turn LEDs on and off.
or know how long it's been since something has happened, etc. There's lots of them, and Addie's just asking us details on all of them.
Yes. Right. I know you enjoy it, Whisker. Okay, so I wanted to clarify this because I had asked if you could DIR, like set specific pins as outputs, like say, so for if you wanted to set pin 0 to 7 as outputs, what you would write is DIRA square brackets 0 to 0 dot 7 close square brackets tilde tilde, and that would set all of those pins as outputs. But I wanted to see if you could set like pins 2, 4, and 6 to be outputs.
Now, Roy, could you do that with by ORing it to a mask or something?
Yeah, well, there's a couple even easier ways to do it in spin. So if Addie, if you go down to page 105 in the manual,
I am there.
You can see right in the middle of the page there, it has a DirA := percent and then a whole bunch of zeros and ones.
Yep.
Percent means binary number in spin.
Yep.
And so that's a 32-bit binary number there, where it's got 32 zeros and ones, one for each bit in the DirA register, which equates to one for each pin in the DirA register.
Okay.
On the IO pins.
So 1 second.
You could.
I explained this to you last week. I don't know if you got it though.
Well, and then because you guys are using a lot of big words like binary and
binary
masks. We are not at a ball, a masquerade.
Right.
I don't even know what a mask is. So a binary number, 1 is true, 0 is false.
Right.
Right?
And when you count in binary, you only have 2 digits, 0 and 1.
Right. And so by stringing them along in a known fashion, you can represent a whole crap ton of numbers.
Yeah, right. But here it's not really being used that way. It is, but you're not thinking of it that way as the human metaphor thing. You're thinking of it as a bunch of on and off switches.
Right. So So the parallax propeller chip has 32 general I/O pins. What?
Yep.
Yes. Okay.
Right.
And if you want to be able to set all of them on or off specifically, you can do this via binary, which is this 1 0 thing, by putting DIRA equals percent to represent that you're gonna say that this is a binary system that we're working with. And then for every pin, which is 32, for every pin you have a number, either 0 or 1. If you set that pin as 0, then that pin is off, is an input, I guess.
Input.
Yeah, an input. If you set it as a 1, it is an output. So if you wanted like pins 0 through 8 as on, but the rest of them off, you would do DIRA percent 1 1 1 1 1.
No.
What?
It's just to clarify, when you do a binary number, the bits are in the order where they go from right to left.
Oh.
So the first
Dang it.
bit is the one all the way over on the right.
What? What
So
do you
you
mean
would
the first
have
bit?
So when you want to do your example,
All the way on the right. Oh, so we're going backwards.
No, we're not going backwards. It's exactly the same as base 10 or decimal, whatever you normally use. It's the same. The lowest, the least significant digit is all the way over on the right hand side.
Oh, okay.
So it's not backwards.
Right. Okay.
It's the same.
I get it. So it'd be let's see, 32 minus 8 is what, 24? So it'd be 24 zeros and then 8 ones for setting pins 0 through 7 as on.
There you go.
Okay. So that's one example, and then another, and that's on page 105 of the
I definitely want to cover one very important thing right here.
What?
The example that you just gave is to set all 32 of them at once with binary. This binary trick will work with your pin whatever to pin whatever trick using the dot dot. So if you want to set pins 0 through 7, so you go DIRA bracket and then 0 dot dot 7 close bracket colon equals and then a percent to say binary.
Mm-hmm.
And then 8 ones and zeros. That works too.
Well, you just jumped the gun.
And that was what we were going to get to on the next page in the manual, page 106, covers that exact
Whisker
case.
just jumped the gun.
Well,
be any number of bits. You could do 2
I'm not
bits
looking at the
or
manual.
15 bits.
Right. So if I wanted to, going back to my original example, if I wanted to set a 2, 4, 6 as outputs, I'd do dir 2 dot dot 6 equals percent and then like 1 0 1 or 0 1 0 1 0 1 or something like that. No, 1 0 1 0 1 0.
Just be 1 0 1 0 1 because you're specifying 6 through 2 through 6.
So
you only need to specify those 5 bits.
Yep, you're right. You are right. Now, what happens if you accidentally give extra numbers like I just did?
You would end up with the wrong value because if you put in an extra digit on there, it's only going to read the bottom 5 of those.
Oh, I see.
Assign it, so you would be offset, and it would give you the wrong results. Your program wouldn't work at all.
I see. So remember, guys, it's
depends on which side you added your
from
extra
right to left.
Your extra numbers to.
Right.
From right to left.
If you added them to the left side, it's not going to change a damn thing.
Right.
Okay.
But if you add extra digits onto the right side, it's going to change what pins are on and off.
I always add a bunch of extra digits onto the side just to confuse Roy.
Okay. All right, we're back to page 23.
Right.
We're back to page. Are you guys still distracted? I'm on a learning roll here, a learning spin here. Okay. So we figured out DIRA.
We skipped InA,
right?
I think so. We should probably go back to that here.
Right.
So
InA is just saying that you want to put into a pin a certain value.
No.
Oh,
InA is reading in. See how it says read only there next to it?
yes.
You're reading the value of the IO pins.
So if a pin is set to an input and you've got a switch attached to it and you wanted to see if the switch was pressed, you're going to use InA to read that.
Right.
There's a lot of other things that you can use InA for. Like if you have a pin switched to an output
Mm-hmm.
and you set it to high or low with your cog to remember something, and then you can use InA to read what it's currently set to.
So like one cog sets it as OUTA, another cog reads it as InA.
Yeah.
Or even the same cog.
Yeah.
Well, that's awfully
Yeah. So there's a
It's
couple
a
little useful
little
things you could use it for, but
tricky.
you know,
gotta
mostly
keep
I
your-
think what you'll probably be using it for out of the gate here is just to do stuff like read switches or talk to things over serial and whatnot.
So that's only like a single switch. Now,
Mhm.
what if I wanted to read the position of a switch? You know,
So if you
like
had-
like a clicky switch, and maybe it could go to like 3 different, like low, medium, high, right?
Well,
know,
that's
that-
more than one switch.
Oh, so that goes
Right.
to 3 different
Electrically,
pins.
that's more than one switch.
Okay, but
Right.
then that goes
So
through
it
3
would go
different
to
pins.
multiple pins on the
Oh.
input. So you would read multiple input pins.
So then
and
it's like
get the values as separate bits
Okay.
in that value that you read.
I don't think I'm
I
really
see.
up to explaining quadrature encoders to Addie today.
no, that's okay.
Yeah.
That sounds like a complicated, a too complicated name for something that's simple.
Well,
right. And it's true,
Really
but
quadrature encoders.
oh,
Did they
well,
come up with an
once you
easier
once you
name?
understand how they work, the name makes a lot of sense.
right.
It's like
Because
a quadratic equation.
Well, it's about flipping, you know, the.
You said you wouldn't talk about it.
Yeah, I know.
All right.
I'm just saying.
We'll actually eventually get you using a quadrature encoder, and then we'll explain it to you then.
Okay, sounds
Yeah,
good.
and thankfully I've written my own drivers for quadrature encoders, so
Okay,
you know I'll be
Yeah.
able to walk you through it very detailed.
okay. So InA and then OUTA.
Okay, so we pretty much already went over OUTA. It's how you would when you set a pin to an output with the DirA. OUTA is how you set it high or low, and you've already done that a bunch in your LED programs.
And we've talked about the fact that they're what do we say? They were ANDed,
No, they're ORed together.
ORed. There you go.
Right.
They're ORed together in the actual circuitry.
So anytime if a pin is
that was weeks and weeks
dubbed
ago.
1 by anybody, then it is a 1.
Yeah, by
By
any cogs.
of
Any
the
cog,
cogs, yeah.
right.
So if you have multiple cogs using the same pin, if any one of them sets it high, it will be high.
Right.
And let's make sure that we're clear here, Addie. The same tricks that you can use for addressing individual pins with InA or with DirA
Mm-hmm.
apply to InA and with OUTA as well. So you can turn more than one pin on and off at a time in a single line. You can read more than one pin at a single time. And this gets extremely useful. This is one of the coolest things that I just think I think it's great because you can do things like on your demo board, you've got those 8 LEDs that you can turn on and off.
Yep.
They're on pins, 16
16 to
through
23.
24 on the old demo board.
Yeah, something like
Okay. Yeah, 16 through 23, you say?
that. Yeah.
Okay, so basically what you can do is you can go out A bracket,
Mhm.
16.23 close bracket, colon equals, and then any 8-bit number, right? So any number between 0 and 255,
Mm-hmm.
and it will print that binary-wise onto those. So
Right.
you know 255 is 1, 1, 1, 1, 1, 1, 1, 1.
Mm-hmm.
So that by printing a 255 over the top of that area in the register, you will turn all 8 LEDs on. So when I'm debugging code, I'll often use those 8 LEDs on the demo board as a debug display to print numbers in binary so that I can see what numbers it's dealing with in the code right there on those lights. She's looking at me like I'm crazy.
Right.
Pretty
Well,
much.
the other way to think about it is like we described earlier. You can actually do the binary number, the percent, with 1, 0, 1, 1, 0, however many, up to 8 for the 8 LEDs on there, and you can turn them on and off all in one line on the program. You don't have to do individual OUTA for each LED.
And of
Well,
course,
that's
that
handy.
binary number is the same as, a decimal number that you're used to. So if you were to take that binary number and just convert it into a base 10 number, like you've used your whole life, it still works the same way as the binary number would.
For turning on and off the pins, yeah.
Okay. I'll have to look at my old code to see how I did, because I know that one of the issues that I came across was that I didn't know that I could. Well, I don't know if I was completely aware that I could turn a bunch of pins on at the same time, but I knew that if I put like instructions for one pin after instructions for another pin, that I would have to wait for that other pin to turn on. You know what I mean? Like I would have to wait. It would have to wait its turn. It couldn't do it instantaneously.
Yeah, there'd be, because you're
So-
writing in spin, there would be a very small delay from one to the next turning
Right. Right. So
on.
I mean, now that I know that I can do this all at once, then
Yeah, it'll make your
That's
code a
good.
lot shorter too.
yeah. Well,
Right.
yeah. I mean, some of my codes are like what 30 some lines just because I'm busy turning LEDs on and off. But like I said, if I can do those all at once, then that'll make it easier.
Mm-hmm.
Right.
I see. Okay.
So, when we were trying to answer you about DIRA, we brought up the fact that you could take a binary number and OR it against the value that was already in DIRA, and the result would change it. And I know you don't really understand that yet, but for those of you out there who do, you can use that trick here as well. So if you want to change all 32 at the same time, but you don't necessarily want to change all of them right now, this particular command, you can do that here by just ORing in there. And Addie's looking at me confused, so I'll just move on here.
I don't understand.
It's just a boolean math or operation there.
Okay.
We're really
look up.
basically going to end up having to teach her a little bit of binary and boolean stuff.
Meh.
She's making noises, but once she gets it, she realizes it's not really very complicated. It's, just a bunch of truth tables.
It's called, instead of 255 being 1111. What? Let me count how many ones. 11111111. It's just 255. Surprise. It only takes
But
three numbers.
it's really handy when you're doing programming to be familiar with boolean math and with binary numbers.
A computer only knows
Binary.
2 digits, so
All right.
to deal with a computer, it's very useful. And that's not even true. There are computers out there that know 3 trinary-based computers, but
Let's get back to
yeah.
spin.
Really uncommon.
You guys, tangent
So-
police. Tangent
back,
police.
Back to page 23 here.
CTRA.
The next set of all the rest of the registers are most of which are used for the counter A and counter B stuff that we covered a few weeks ago.
Okay.
Basically, these are the registers where you can configure how those counters work, and the frequency and the phase are additional parameters in how they operate.
Oh.
So the control, we can go into more detail when we actually do an example that uses these.
Sure.
But basically, your control register is configuring how it works, like whether it triggers on, a pin going high or a pin going low and stuff like that, and which pin it listens to count.
Okay.
And then the frequency and phase are just used for, how much to increment and the stuff like that. It's a little more advanced stuff like we talked about a while ago that can be done and we'll cover that in more detail. And then the last two there, the VCFG and the VSCL, are for configuring the video output stuff that we talked about a
Okay.
few episodes ago also.
And I imagine that
And-
if we were to look these
Right.
up specifically, we'd see all the different tables involved and
Right.
modes and all that stuff.
Right. And
Okay.
again, when we get to an example where we're going to use a counter, which will probably be in a few episodes from now, then we'll go over these in more explicit detail, explaining what to set in each register to get the result we want.
Okay.
So what you mostly need to pull out of the table there is that these are addresses in cog memory, and you can interface directly to them with your code to do all sorts of special things.
Right.
And I think it's interesting so that each cog has this in it.
Mm-hmm.
Right.
And so it's what is that?
You've got 8 of them.
Not mutually exclusive. It's common memory
Well,
or whatever,
well,
kind of.
the common stuff is really just the counter and then the in, out, and direction registers. Those are common to all the cogs.
Okay.
The counters, each one has their own set of counters.
They're not
Right.
and their
sharing.
own set of video configuration stuff. So they aren't common. They're unique
Yeah,
to
okay.
each cog,
Okay, I get it. I get it.
right?
Yep. Cool.
So
Okay. So then each cog can have different. Well, I mean, I guess never mind. That was a dumb question.
no, it's not.
I mean, a
question.
dumb question that I never asked, but yeah, okay. Okay.
Yeah, each cog can have its own counter configuration, and each cog could be driving a different video display. If you physically had 8 different displays plugged in to the I/O pins, using up all the I/O
Cool.
pins, you could drive all 8 of them, one from each cog.
Cog Wars.
Or like me, I use SIDCOG to generate musical tones, and I can have, so many on each cog, but then I go on different cogs to get more and more of them. So I'll
Right.
be running, 4 SIDCOGs in different cogs, and I get a lot more voices that way because I can make better use of these kinds of resources.
Right. The SID cog is using these counter registers to drive the pulse width modulation output to produce sound.
Gotcha. Okay. We can go on to the next thing. I think I'm comfortable with that.
Okay.
So each special purpose register may be accessed via its physical register address, which I imagine is the complicated $.
Yeah, that's
Something.
hexadecimal address. You can also use the decimal version of those numbers, but those hexadecimal is typically what's used.
Okay. Okay, so let me so for instance, if
I'll
I
have
wanted
to teach
to
Addie hex.
Nope.
Yeah.
Nope.
Yeah,
Nope.
you'll need to know it.
Nope.
I think it's outside the scope of the show, but I think I'm definitely going to have to teach Addie binary and hexadecimal.
Nope. Okay, so
They're very easy.
Addie is asking the questions here, determining the content. Okay, so when I set pin 16, for instance, to tilde, right? DIRA 16 tilde, I can also do $1F6 16 tilde.
No, that's only in propeller assembly can you use those specific addresses directly.
Okay, then
You in spin you have to use either the name, which is listed there.
Yep.
In the name column.
Yep.
Or there's a command in spin called SPR, which is special purpose register. And then index of 0 to 15, which is these 15 special purpose registers. So you could use that instead.
Well, that's just complicated.
It's just an alternate way of doing it, and they show you down there.
Why would
probably
people
end
wanna
up
use
just
that?
using their names, honestly.
Well, I mean, yeah, obviously, because it makes more human sense, but why would anybody use...
Well,
So the PASM aside, why would anybody use
I'll answer you. Any time that they give you the ability to use a number instead of, a list of things that are accessible in the same place with an index number of them, allows you to access them with an algorithm from one line instead of multiple lines. So you can have a repeat, index, from 0 to how many registers were there?
15. 16?
60. So 0 through 15.
Oh, yeah, 16.
Repeat index from 0 to 15, and then your, what is it, SPR?
Right.
Uh-huh.
And then, is it a bracket in this case?
Yeah, same thing.
And you're using a bracket index, okay? And then, if you use a case statement, you can go through each one of them, and depending on which one you're on, it can do a different thing on each iteration of the loop.
Right. Another example is you could write code that could work with counter A or counter B, and then you could pass it in a number 0 or 1, and then use the SPR access mechanism to access the counter A, frequency A, and phase A registers, but you're accessing with SPR, but then you could also add in your passed in parameter, which is a 0 or 1, which would cause it to then access, if it's a 1, it will access counter B instead of counter A.
So basically what it
Via the
boils down
SPR.
to is that you can design it so that your algorithm that's doing whatever you're doing is more flexible and responsive to different types of situations. The less and less it's hard-coded, the more and more flexibility is possible.
Crickets, and I leave that to you guys. Okay. I will use
It's kind of an advanced usage that,
I will use its predefined name, no problem.
yeah, most code I've seen in Spin just uses the name of the actual registers.
Gotcha.
It's really uncommon to use the SPR notation.
Okay.
And hopefully Roy and I just inspired somebody to use the thing. The poor guy never gets his time in the sun.
Alrighty. Hub. To maintain system integrity, mutually exclusive resources must not be accessed by more than one cog at a time. Because it's not capable of it. Right. It controls access to mutually exclusive, giving each cog a turn, round robin fashion, at half the system clock rate. Right. So it gives cog access. Okay, this means that the hub gives a cog access to mutually exclusive resources once every 16 system clock cycles.
Right.
Once every.
So each cog will get access to the hub once every 16 cycles.
So it takes 2 clock cycles per cog. Because there are 8 cogs.
Well, you shouldn't really think of it that way. Just think of it as when the hub is on cog 0
Mm-hmm.
and then moves off, it will be back to cog 0 16 clocks later.
Okay.
And the reason why you shouldn't really think of it as it takes 2 clocks is because it's not really taking 2 clocks. It's more like that cog is given access every 16 clock cycles, and if it doesn't do anything, it'll just go on to the next cog, and if it does something, it'll actually interact with the hub then and issue a command, and the hub will operate.
But only for one long.
For one long's worth of passing back and forth, or there's all these other commands that get issued here. There's cog new.
That would still have to be.
We talked about all of this stuff
cycles.
Before.
I mean, that would still have to be within 2 system clock cycles, though.
Everything happens in one, really. I mean, there's like stop and go kinds of stuff that make it to your code seem like it takes longer, but literally everything happens in one clock cycle. Sometimes it just takes more than one
hub go round
to make it really happen, right? Because it's more complicated than what a 32-bit processor can do in one step, right?
Okay.
Like you literally a long is 32 bits, and literally the cog has 32 bits that it can send to the hub and back. Remember, we were talking about a couple weeks ago how when that hub is turning around, it checks the electrical bits on a cog to see if there was a cog new or anything like that.
Yeah.
that's, related to what you're asking here.
Well, I know.
Right. And if you get to the top of the very next page, it has a little graph showing the system clock versus the hub clock and versus the cogs having access to hub. And it's kind of it looks complicated, but it's not really that bad. So across the top there, you've got your system clock going by.
So it is 2 clock
0
cycles. Ha.
Right. So a hub clock is 2 clock cycles per 2 system clock cycles per one of its clock cycles. And it's two cycles go by before it gets to the next hub, the next cog having access to the hub. But if you'll notice, cog 0 is actually operating on the hub for up to 8 clock cycles, because that's how long those instructions take.
So
Right.
how does it do that if it doesn't have access to it?
Well, it's a little bit complicated, but what happens is that it initiates the command and says, okay, I want to read memory. Okay. But the result isn't given back to it until 8 clocks later.
Do you remember when like I was just saying, how that when the hub gets around and it checks the cog to see what the cog is asking to do, the
Yeah.
cog just sits there after it's sent that, it doesn't really send it. It turns on, these 32 switches, right? Some
Yeah.
of them. That's how it talks to the, the hub. It turns them on. The hub sees that when it comes around, and then it starts doing that job.
Right.
And then when it's done, it, tells that cog that I'm done. Here's what you asked for.
I see.
Right.
So it might take.
And your table right there is showing you how long that actually takes to do.
Right. And so, even though you issued on clock 0 hub, the cog 0 issued a command to the hub. And that's what HI is hub instruction, is what that's saying there on that little
I see.
graph.
Yep.
So it's issued a hub instruction, and the hub instruction starts going, and then the hub access window moves along, and 2 clocks later it gets to cog 1, and cog 1 in this case doesn't do anything, doesn't start anything happening.
So
But
okay,
in the background, the cog 0 hub instruction is still executing. And
Right.
eventually it
Okay.
gets done 8 clocks later, and the result is available for cog 0.
Right. So cogs can initiate instructions that run in the background of the hub, even though the hub is moving from cog to cog.
Right.
And when the cog
Run
is
to the background is a loose term, but that's close enough to
Yeah.
not
Okay.
matter.
Yeah,
Okay.
I would have to ask Chip for details, but as I've said on the show before, I'm assuming that there's dedicated circuitry for every single one of the cogs in that hub to do all of those jobs, and
Yeah.
that's why it can do 8 of them at the same time. All it's taking turns on doing is going around and saying, "What do you need? Okay, now what do you need? Okay, now what do you need?" But each one of them internally in the hub has its own copy of.
Oh, the hub's like a nurse.
Yeah, basically. Yeah.
I wouldn't say it's a full copy. I would say some portion of it is
Yeah.
unique to each cog, and then the part that's actually doing the final step of loading up the RAM into the cog's bus or whatever is where you end up with it's only got one of those, but the window for that cog is where it sticks that in.
So to close that up, because we're out of time here, Addie, the main thing to take away from that is that when you're asking to do in a cog, you're asking to do a hub instruction like that,
Yep.
your code is going to pause while it waits for the answer.
Okay.
Right. And
So-
all of this is somewhat meaningless to spin because we don't even really care. This is mostly for PASM.
Maybe you should be first PASM.
Well, they're related. They're part of the
I seem
same
to be
thing.
asking more questions about it.
It's just helpful to know what this is going on under the covers.
Right.
That's all.
Right.
All right. That's it for us for this week. Hope you guys enjoyed it. Next week, we're all going to learn binary and hexadecimal.
No.
Not really. But if you want to do some homework, do that. You can get this show every week on Tuesday at firstspin.tv.
Yep.
Bye.
Bye.
Yeah.